Hey everybody, 5.4. Let's check it out. Now that we know the fundamental theorem of calculus, the world is our oyster. Okay, so let's check out indefinite integrals and net change. So it turns out these two ideas here in 5.4 have nothing to do with one another. I suppose neither of them, it's simply that neither of them warrants its own section because they're not, neither idea is all that involved or long to discuss, particularly indefinite integrals. So we're going to get to that first. We've talked about definite integrals. What is an indefinite integral? An indefinite integral would appear just the same as a definite integral with one big difference, I guess. Looking at it here, notice anything missing, right? There's no numbers at the bottom or top of the integral sign. There's no a and b. If there are no numbers, then you've got an indefinite integral. Well, what would you do in that case, right? So you notice what we have on the right-hand side here. We have the antiderivative capital F of x plus c. We won't have any numbers to plug in. If you don't have any limits of integration, it's simply asking you to find the general antiderivative. Thinking back, right, we learned the general antiderivative back in 4.9. We did not introduce any new notation at that point. We saved the integral notation for when we started discussing the definite integral in chapter 5. So it turns out that there is no special notation for an antiderivative. It's simply write an integral sign, just don't put limits of integration on there because you're not going to plug any numbers in. So there you go. People figured that worked good enough for them. If you don't see any numbers, it means to take the antiderivative. So let's take a look at some examples. We really don't need to do much here because we talked plenty enough about finding antiderivatives back in 4.9, and we've even done more of them right in 5.3 and so on. We'll practice these a ton, but just to see the notation, let's take a look here. How about this? Find the indefinite integral, part A. We would read that. You'd probably just say the integral. Find the integral of 3x to the 5th minus e to the x plus 1 dx. And again, just a matter of finding the antiderivatives. So 3x to the 5th, that'd be x to the 6th. 3 over 6 would be 1/2 x to the 6th. Okay, anyway, here's the answer. 1/2 x to the 6th minus e to the x plus x. And here we do include the plus c. Okay. Let's try one more. Hey, how about some trig? How about the integral of secant squared t dt? You may remember secant squared is the derivative of tangent. So this antiderivative would be tangent t plus c. Okay. That's it. That's indefinite integrals. So now let's move on to net change. Net change, like I said, totally different idea. This is back to definite integrals. So let's take a look here. The net change theorem. The net change theorem says the definite integral of a rate of change is the net displacement. Okay, this is our first mini immediate application for definite integrals or for integration in general. If we are integrating a rate of change, so here we're thinking of f of x, the little f of x, as a rate. We find the definite integral of a rate of change that is equal to net displacement. What does that mean? Okay, so if you take a look at your that definite integral there, here's what we're saying. F of x is a rate that means when we find capital F of B minus capital F of A, that represents displacement. What does this even mean? It could mean a lot of things. It's not, it's going to be more general than what I'm about to share, but let's connect it to something we're familiar with derivatives. A rate, let's think like a velocity. What if f of x was to represent a velocity? If we did an integral of that, we'd be taking an integral of a rate of change, right? What would that imply about our answer? Well, what is the antiderivative of a rate? Or actually, what is the antiderivative of velocity? We'd be moving backwards. It would get us back to position, the original function, if you will. So capital F of x would be the position function. Okay, well, what would that mean about capital F of B minus capital F of A? The A and the B are usually going to represent time. So B is the ending time and A is the starting time, right? Where does it start? Where does it stop? Okay. Well, if you found capital F of B, that is the position at the ending time, or you might just say that's the ending position. Capital F of A is the position at the beginning time, or you would probably just say it's the beginning or the starting position. So ending position minus starting position. That would tell you how far you've gone, how far you've traveled. Where are you at the end? Subtract where you were at the beginning. That's how far you went, the displacement, if you will. Let me explain this in a picture. We did this in a previous section, but we're going into just a little bit more detail with it now. Let's take a look at just this sort of graph that I sketched. You can see here on the y-axis, we've got miles per hour, and on the x-axis, hours. So this graph tells you how fast something is moving at any given time. I sort of, you might think of this as being like a long car ride or a trip across town or so, maybe further than that. So, at first you haven't gone anywhere. It's like 0 hours because it's your starting time and the car is sitting still. And then you start to move, but you're driving kind of slowly. And then maybe you get on the freeway and you're driving faster. Okay. And then for whatever reason, maybe there's traffic, there's gridlock, there's a bottleneck somewhere, and you really slow down almost just to a crawl. So you're really slowed down. You're really moving very slowly for a few minutes there. And then the traffic clears and you're moving, at a decent speed again. And then you exit the freeway and then you make it to your destination and you stop. What would this area, all that area, represent? And it turns out, we can see it right here, the area is the miles traveled. Why is that? Well, if we think about the area, just as simple as base times height or length times width, we've got miles per hour times hours, and it gives us miles. So there you go. That's pretty cool. Okay. I want to talk through this. I want to sit a little bit more on this. Forgot I had this to mention. What if we also, so back here, we thought about the total area, right? What if we didn't want to do the total area? What if we only wanted to do a section and how far we traveled during this section? If we did something like this, just from maybe the 1 hour mark to the 2 hour mark. Well, no problem. We could fill that in, just this area, and find only the miles traveled here. What would that mean in terms of our integral? These are the values of A and B, right? There are values along the x-axis from 1 to 2. We're finding that area. And so it represents just how many miles we traveled, maybe from the 1 hour mark to the 2 hour mark, that sort of thing. Okay, let's stop this video here. We've introduced the net change theorem. We're going to get to some examples next.